You know that the p block elements are placed to the right side of the periodic table in groups 13 to 18. You also know that in the atoms of p block elements, the differentiating electron enters the valence p subshell. Thus, in these elements, the NP subshell is gradually filled. On account of this, the general valence shell electronic configuration of these elements is NS2, NP1 to 6. Note that the electronic configuration of helium is 1s2. Although helium does not have p orbitals, it is a p block element because it resembles that of other p block elements of the 18th group with respect to their properties. Most p block elements are non-metals, while the remaining are metals and metalloids. Thus, the presence of all the three types of elements in p block of the long form of periodic table bring diversification in chemical behavior of these elements. The study of these elements is an important area in chemistry, as these elements and their compounds have immense significance in industries and day-to-day life. Now let us turn to the study of group 15 elements. Let's first discuss the occurrence of these elements. The elements in group 15 are nitrogen, phosphorus, arsenic, antimony, and bismuth. Nitrogen is the major constituent of the Earth's atmosphere and accounts for 78% of it by volume. It is the first member of this group and occurs in free state as a diatomic gas, N2. No other element of this group exists in free state. In combined state, it mainly occurs in the form of minerals such as Chile salt Petri and Indian salt Petri. It is also found as the essential constituent in proteins, amino acids, nucleic acids, and enzymes. The next element in the group is phosphorus. It is the 11th most abundant element in the Earth's crust. Being a very reactive element, it does not occur in free state in nature. In combined state, it occurs in the form of minerals as phosphates. Chloropatite, fluorapatite, and hydroxyapatite are some examples of phosphates. These comprise the apatite family. Phosphorus is an essential constituent of plant and animal matter. Phosphate groups are among the important constituents of nucleic acids, that is, DNA and RNA. About 60% of bones and teeth are composed of phosphates. Phosphoproteins are present in egg yolk, bone marrow, and milk. The remaining elements of the group, that is arsenic, antimony, and bismuth, mainly occur as sulfides. For example, arsenopyrite, stibnite, and bismuth glands. Now let's look at the electronic configuration of group 15 elements. The differentiating electron in these elements enters the NP subshell. Hence, the valence shell electronic configuration of these elements is Ns2Np3. So, it is evident that these elements have 5 electrons in their valence shell. The electronic configurations of these elements are listed in the table here. Due to the exactly half-filled electronic configuration of the NP subshell, the elements of this group are fairly stable. For example, dinitrogen is an inert gas under normal conditions. Now, let's look at the trends of some atomic properties of group 15 elements, such as atomic and ionic radii, ionization enthalpy, and electronegativity. A comparison of these two tables shows that as we move down the group, the atomic radii, covalent radii, and ionic radii increase due to the addition of a new principal energy level in each successive element. There is a considerable increase in the covalent radius from nitrogen to phosphorus. This is due to the effective shielding of the s and p electrons present in the penultimate shell of phosphorus. However, from arsenic to bismuth, there is only a small increase in the covalent radius due to the poor shielding effect of the d electrons of the penultimate shell in arsenic and antimony, and the poor shielding effect of the f electrons of the antipenultimate shell in bismuth. As a consequence, the effective nuclear charge increases, which leads to a small increase in the covalent radius from arsenic to bismuth. Now let's look at ionization enthalpy. Group 15 elements show higher values of ionization enthalpy as compared to group 14 elements. This is due to their higher nuclear charge, smaller atomic radii, and stable half-filled electronic configurations. However, as we move down the group, the value of ionization enthalpy decreases. This is due to the gradual increase in the atomic size, which reduces the force of attraction between the valence electrons and the nucleus. Finally, let's look at electronegativity. You know that electronegativity is the tendency of an atom to attract a shared pair of electrons more towards itself. The values of electronegativity of these elements are listed in the table here. As you can see from the table, the electronegativity decreases gradually on moving down the group from nitrogen to bismuth, due to the corresponding increase in the atomic radii. Note that after fluorine and oxygen, nitrogen has the highest electronegativity. Let's first study the physical properties of group 15 elements. Physical properties include physical state, metallic character, melting and boiling points, density, and allotropy. Let us look at each in turn. Nitrogen is a diatomic gas, while the remaining elements are solids. You know that as you move down a group, metallic character increases. The same trend is observed for group 15 elements too. Do you know the reason? Try to answer this question on your own before looking at the answer. As you move down the group, the ionization enthalpy of the elements decreases with an increase in their atomic size. In other words, the effective nuclear force of attraction on the valence electrons decreases down the group. As a consequence, the metallic character increases down the group. The first two elements of this group, nitrogen and phosphorus, are non-metals, and the next two, arsenic and antimony, are metalloids, while bismuth is a typical metal. Next, let's look at the trends in melting and boiling points. The melting point increases from nitrogen to arsenic due to the gradual increase in atomic size. The very low melting point of nitrogen is due to its discrete diatomic molecules. On the other hand, the high melting point of arsenic is attributed to its giant layered structure, in which the layers are closely packed. However, although the atomic size increases from arsenic to antimony, there is a decrease in their melting points. Although antimony has a layered structure, it has a low melting point than arsenic because of the relatively loose packing of atoms. Furthermore, the melting point of bismuth is less than antimony due to the loose packing of atoms by metallic bonding. On the other hand, the boiling point gradually increases from nitrogen to antimony, as shown in the table here. Next, let's look at the trend in the density of group 15 elements. The density of these elements increases regularly from nitrogen to bismuth. Finally, let's look at allotropy. All the elements in group 15, except for bismuth, show allotropy. Nitrogen exists in two allotropic forms, that is, alpha nitrogen and beta nitrogen. Phosphorus exists in many allotropic forms. Of these, the two important allotropic forms are white phosphorus and red phosphorus. Arsenic exists in three important allotropic forms: yellow, grey, and black. Antimony also has three important allotropic forms, namely yellow, explosive, and metallic. Let's now discuss the oxidation states of group 15 elements. Let us begin with negative oxidation states. You know that all the elements of group 15 have 5 electrons in their outermost orbit. Hence, they need only 3 electrons to complete their octet and attain noble gas configuration. The octet can be achieved either by gaining 3 electrons or by sharing 3 electrons by means of covalent bonds. As a result, the common negative oxidation state of these elements is -3. However, as we move down the group, the tendency to exhibit -3 oxidation state decreases. This is due to the increase in atomic size and metallic character. Only nitrogen atoms can gain 3 electrons from highly electropositive metals like lithium, and magnesium to form ionic nitrides. Note that a huge amount of energy, about 2125 kilojoules per mole, is required to form a nitride ion, that is, a N-3 ion. In spite of the huge amount of energy required, electron gain takes place in nitrogen because it is the smallest and the most electronegative atom. In other words, the nitrides formed are stable because the 3 electrons gained by the nitrogen atom are much closer to the nucleus. Examples of nitrides include lithium nitride, magnesium nitride, and calcium nitride. Compounds such as sodium phosphide and sodium bismuthide are also known, but these are not ionic. Nitrogen and the remaining elements of this group form covalent bonds and show a formal oxidation state of -3. For example, calcium phosphide and hydrides such as ammonia, phosphine and arsine. Owing to the gradual decrease in their electronegativity and ionization enthalpy, we can conclude that the tendency of these elements to show -3 oxidation state decreases down the group from nitrogen to bismuth. Nitrogen also shows -2 oxidation state and -1 oxidation state. -2 oxidation state is observed in hydrazine, while -1 oxidation state is observed in hydroxylamine. Apart from negative oxidation state, group 15 elements also show positive oxidation states of +3 and +5 by forming covalent bonds. However, due to the inert pair effect, or the tendency of a pair of s electrons to remain inert, the stability of +5 oxidation state decreases down the group, while that of +3 oxidation state increases. Note that bismuth pentafluoride is the only stable compound of bismuth known in its +5 oxidation state. You know that nitrogen is an element of the second period. Therefore, it has only s and p orbitals, but no d orbitals in its valence shell. Therefore, nitrogen can show a maximum covalency of 4 as there are only 4 orbitals available for bonding. A covalency of 4 is obtained by sharing its lone pair of electron with another atom of a molecule or ion. Therefore, nitrogen cannot exhibit a covalency of more than 4. For the same reason, it doesn't form pentahalides like NCl5 or NF5. However, phosphorus and the remaining elements can exhibit a covalency of 5 and a maximum covalency, also called expanded covalency, of 6. This is possible because of the presence of vacant d orbitals in the valence shell. The compounds of phosphorus and the remaining elements that show a covalency of 5 and 6 are listed in the table here. All the compounds of group 15 elements, which exhibit a +5 oxidation state, are covalent. However, in case of +3 oxidation state, both ionic and covalent compounds are formed. For example, bismuth trifluoride and antimony trifluoride are examples of ionic compounds. Similarly, nitrogen trichloride, phosphorus trichloride, and arsenic trichloride are examples of covalent compounds. In other words, the ionic character increases from nitrogen to bismuth due to the increase in the metallic character of group 15 elements. We can thus conclude that in group 15 elements, the covalent character decreases from nitrogen to bismuth. Talking again about nitrogen, because of its smaller size, high electronegativity and strong tendency to form p-pi multiple bonds, it exhibits various oxidation states from -3 to +5. Let us look at the wide range of oxidation states of nitrogen in its compounds. Nitrogen has an oxidation state of -3 in ammonia, -2 in hydrazine, -1 in hydroxylamine, 0 in dinitrogen, +1 in nitrous oxide, +2 in nitric oxide, +3 in nitrogen trioxide, +4 in nitrogen tetroxide, and +5 in nitrogen pentoxide. In case of nitrogen, all oxidation states from +1 to +4 tend to disproportionate in acid solution. You know that a reaction in which the same element undergoes both oxidation and reduction is called disproportionation. For example, nitrous acid tends to disproportionate into nitric oxide and nitric acid, as shown in the equation here. Similarly, in case of phosphorus, nearly all intermediate oxidation states disproportionate into +5 and -3, both in alkali and acid. For example, phosphorus acid tends to disproportionate into phosphoric acid and phosphine, as shown in the equation here. You know that generally, the first element of any group differs from the rest of the elements with respect to their properties. The same anomaly is reflected in group 15 elements. The first element in the group, nitrogen, differs from the rest of the elements in its properties. The unique properties of nitrogen are attributed to its small atomic size, high electronegativity or high ionization enthalpy, the non-availability of d orbitals, and the propensity to form multiple bonds. Only nitrogen can form nitride ions by gaining electrons due to its small size and high electronegativity. For example, lithium nitride and magnesium nitride. Nitrogen, being smaller in size, can effectively form p-pi bonds with other atoms of itself and atoms of other elements with a small size and high electronegativity, such as oxygen and carbon. The other elements do not form p-pi bonds because of their relatively larger size. In other words, the p orbitals of these elements are larger in size and, therefore, sideways overlapping will not be effective. The tendency of nitrogen to form p-pi bonds is one of the major features that distinguishes it from phosphorus and other group 15 elements. As nitrogen can form strong p-pi multiple bonds, it exists as a diatomic molecule with a triple bond between the two atoms. You know that this diatomic molecule is dinitrogen. The bond enthalpy of a triple bond being very high, about 941.4 kilojoules per mole. Dinitrogen is inert at ordinary conditions. For the same reason, it forms several compounds, such as nitrates, nitrites, azo and diazo compounds, oxides, oxoacids and cyanides. You know that in these compounds, nitrogen shows varied oxidation states. On the other hand, the other elements in the group, such as phosphorus, arsenic, and antimony, exist as tetraatomic molecules, as represented here. In all these molecules, only single bonds are present between the atoms. Note that bismuth forms metallic bonds in its elemental state. The catenation tendency is less for nitrogen when compared to the other elements of the group. This is because the single bond between nitrogen atoms is much weaker owing to the higher interelectronic repulsions between the lone pair of electrons present on the nitrogen atoms. The high interelectronic repulsions in dinitrogen are attributed to its smaller bond length or small size of nitrogen atoms. The maximum length of the chain observed for nitrogen is 3 in azide ion. Nitrogen doesn't form d-pi, p-pi bonds due to the absence of d orbitals. By contrast, heavier elements like phosphorus can form d-pi, p-pi bonds as seen in phosphorus oxochloride and triethyl phosphate as shown here. For the same reason, that is, due to the absence of d orbitals in nitrogen, it cannot form d-pi, d-pi bonds. Due to the availability of vacant d orbitals in the remaining elements of group 15, compounds of these elements, such as triethylphosphine and triphenylarsine, form d-pi, d-pi bonds with transition elements. Vacant d orbitals present in the phosphorus and arsenic of triethylphosphine and triphenylarsine accept electron density from filled transition metal d orbitals and form d-pi, d-pi bonds as shown here. Let us look at the trend in the chemical reactivity of group 15 elements towards hydrogen, oxygen, halogens and metals. Let us begin with their reactivity towards hydrogen. All the elements of group 15 form hydrides of the type EH3, where E can be nitrogen, phosphorus, arsenic, antimony or bismuth. They are named as ammonia, phosphine, arsine, stibine and bismuthine. Let us now study the gradation in chemical reactivity of these hydrides with respect to stability, reducing power, basic character and boiling and melting points. The table here shows that the bond dissociation enthalpy of hydrides decreases on descending the group, which further indicates that the stability of hydrides decreases from ammonia to bismuthine. This is because the central atom E increases in size down the group. With the increase in the size of the central atom, the EH bond becomes weaker. In other words, with the increase in size, the overlapping between the orbitals of E and hydrogen will not be effective. This accounts for the decrease in the stability of hydrides as we move down the group. Hydrides of group 15 elements are strong reducing agents. The reducing character of hydrides increases from ammonia to bismuthine due to a decrease in the strength of the EH bond down the group. Hence, bismuthine is the strongest reducing agent among all the hydrides of group 15 elements. These hydrides are basic in nature. They act as Lewis bases due to the availability of a lone pair of electrons on the central atom. However, their basic character decreases down the group with an increase in the size of the central atom. With the increase in size, the lone pair of electrons gets dispersed over a large area of the central atom. Thus, the tendency to donate the lone pair of electrons gradually decreases. The decreasing order of the basic nature of hydrides is represented here. It is apparent that ammonia is the strongest base of all hydrides. As you can see from the graph, the boiling point of hydrides decreases from ammonia to phosphine and then increases from phosphine to bismuthine. Note that there is a sharp decrease in the boiling point as we move from ammonia to phosphine. How do you account for this? It is because of the presence of intermolecular hydrogen bonding in case of ammonia. In other words, as ammonia molecules are associated through hydrogen bonding in liquid state, it has a higher boiling point than phosphine. Further, as we move down the group from phosphine to bismuthine, the increase in boiling point is attributed to the increase in their molecular weights. Note that the same trend is observed for their melting points. Next, Let's take a look at reactivity towards oxygen. Group 15 elements form two types of oxides, that is, E2O3 and E2O5. You know that nitrogen shows a strong tendency to form p-pi bonds with oxygen. As a consequence, nitrogen forms a wide range of oxides. Nitrogen forms 5 stable oxides, as shown here, exhibiting oxidation states ranging from +1 to +5, while the other elements form oxides only in +3 and +5 oxidation states. Bismuth can't form oxides in +5 oxidation state because of the inert pair effect. The lower oxides of nitrogen, such as nitrous oxide and nitric oxide, are neutral, while the higher oxides, such as dinitrogen trioxide, dinitrogen tetroxide, and dinitrogen pentoxide, are acidic. Oxides in the higher oxidation state of an element are more acidic than that of the lower oxidation state. Hence, the acidic strength of oxides of nitrogen increases from dinitrogen trioxide to dinitrogen pentoxide. As we move down the group, the acidic character decreases. In other words, the basic character of oxides increases on moving down the group. The oxides of nitrogen and phosphorus of type E2O3 and E2O5 are acidic, whereas the oxides of the type E2O3 of arsenic and antimony are amphoteric, and those of bismuth are wholly basic. Now let's look at reactivity towards halogens. All the elements of group 15 form trihalides and pentahalides with the general formula EX3 and EX5. Here, E may be nitrogen, phosphorus, arsenic, antimony or bismuth, while X may be fluorine, chlorine, bromine or iodine. For example, NF3, PF3, ASF3, SBF3 and BIF3 are trihalides. All the trihalides of these elements, except those of nitrogen, are stable. In case of nitrogen, only nitrogen trifluoride is stable. Nitrogen trichloride, nitrogen tribromide, and nitrogen triodide are unstable due to the large difference in the size of the nitrogen and halogen atoms, which weakens the nitrogen-halogen bond. Phosphorus, arsenic, and antimony form pentahalides due to the presence of vacant d orbitals in their valence shells. Nitrogen does not form pentahalides due to the absence of a d orbital in its valence shell. Pentahalides are more covalent than the corresponding trihalides. Moreover, the covalent character of halides decreases from nitrogen to bismuth. Note that bismuth trifluoride is not a covalent compound. All the elements of group 15 react with metals to form their binary compounds, showing -3 oxidation state, with the general formula M3E2. Here, M stands for metals such as calcium, magnesium, or zinc, while E stands for an element of group 15. For example, calcium nitride, calcium phosphide, zinc antimonide, and magnesium bismuthide.